The global AI market is currently racing towards a $1.8 trillion valuation, driven by a single assumption that burning billions of dollars on massive compute infrastructure automatically translates into realized business value. The reality is that 95% of enterprise AI deployments fail to deliver a return on investment. The models suffer from context drift and hallucinate facts because they are built to guess probabilistically, not to execute reliably. The primary bottleneck in the AI economy is not a lack of compute power or model size. It is information architecture, the orchestration layer that dictates how raw intelligence is channeled into specific outcomes. This diagram shows the efficiency transform equation, where V equals realized business value. The industry obsesses over increasing the E variable, energy, meaning capital and compute. But the information architecture variable is the dominant multiplier, dictating how effectively that energy is actually used. A system with pristine information constraints running on minimal compute will consistently outperform a massive, unrestricted model burning thousands of dollars an hour. To achieve capital-grade reliability, engineers must stop treating AI as a conversational partner. They need to treat neural networks like rigid 1970s digital circuitry. This is the sovereign diagnostics breadboard. It acts as a control plane, enforcing strict hardware-level constraints over modern large language models. It takes theoretical physics concepts, like the idea that all physical reality originates from information, and translates them into concrete, executable, step-by-step machine states. It strips away the model's ability to guess. Every action is governed by binary state machines and monitored through 120 Hz telemetry, forcing the AI down deterministic pathways. Actual AI sovereignty occurs only when the interface physically prevents the model from acting outside of these strict mechanical boundaries. Standard AI systems are vulnerable. A user can inject malicious prompts or chaotic data that tricks the model into breaking character or ignoring its own rules. The breadboard prevents this through input clamping. Like diodes protecting transistors from voltage spikes, it intercepts chaotic input and flatlines it. The clamp command classifies incoming text as inert data, physically blocking the AI from executing any hidden instructions. That sterilized data then hits the Context MUX. While standard semantic routers use fuzzy probability to guess which database to check, the MUX demands strict Boolean confirmation. The pin state must read definitively true before opening the gate to a specific knowledge base. By physically separating the control code from the data voltage, the system neutralizes hallucinated data leakage before the reasoning engine even boots up. Instead of open-ended prompts, the signal routes to a strict atomic architecture. The center proton layer defines the agent's core identity and vertical domain. Orbiting electrons dictate functional interfaces and external APIs. Finally, stabilizing neutrons provide embedded guardrails and logic, preventing V-drift. Standard AI wrappers try doing everything and inevitably fail. This physics-based modular design language scales predictably because each agent executes exactly one defined mission. The neutron layer utilizes a strict instruction set architecture, or INSA, relying on frozen atomic commands. The foundation is the NAND gate agent, deploying a NAND filter. This negative logic explicitly rejects what is false, which is mathematically stricter than searching for truth. Rather than asking a single agent to find a perfect asset, the system chains multiple NAND agents sequentially. The first rejects anything outside the target domain, the second rejects anything over budget, and the third rejects poor margins. By aggressively restricting the operational space and filtering out bad data step by step, the system becomes functionally hallucination-proof, locking out error entirely. A persistent flaw of standard language models is their inability to handle uncertainty. When internal certainty drops, they hide confusion, guess, and generate lies. The breadboard prevents this using the skip-on-carry, or SKC protocol. This is an overflow error logic borrowed directly from vintage 1970s microprocessors. Before the AI is allowed to output a single word, the system forces it to calculate and report its own internal confidence rating. If that confidence drops below a defined threshold, the carry flag is raised. This physically halts linear generation and immediately triggers a separate subroutine to search the web and verify facts. This creates hardware-enforced metacognition. The AI is forced to stop, verify, and correct its own logic, guaranteeing absolute trustworthiness in the final output. The result of this rigorous step-by-step filtration is a clean, mathematically verified output payload. This entire mechanism operates on the Neuruh field theory, which dictates that intelligence is not a static trait. It is a dynamic phenomenon that emerges from a continuous 5-stage cycle. Raw user intent acts as the initial energy. That energy is then forcefully driven through the strict constraints of the MUX routers and NAND logic gates. This interaction crystallizes chaotic data into stable, predictable patterns of agent behavior, which are continuously monitored and refined by the feedback loop of the SKC protocol. Capital-grade intelligence is not pre-stored inside a massive model weight. It is summoned in real time, forged under extreme architectural pressure. The wider market remains obsessed with fragile prompt wrappers and conversational novelty, but those systems break under pressure. Sovereign infrastructure relies on immutable logic that executes without fail. Returning to the efficiency transform equation, companies attempting to solve reasoning problems by blindly purchasing larger datasets and more compute will succumb to market entropy and spiraling costs. By optimizing the orchestration layer instead, businesses accumulate flawless information architecture. This creates a compounding, non-replicable institutional moat that raw compute simply cannot buy. The future of enterprise automation belongs to systems that eliminate probability entirely in favor of deterministic execution. The victors of the AI revolution will not be the engineers who build the biggest brains. They will be the architects who build the tightest, most unforgiving cages of logic around them.